Okay, so last time we started talking about curvilinear motion. We talked about x, y, the Cartesian coordinate system. We talked about the what else? The tangent and normal. And we said that the Cartesian coordinate system fit perfectly if you have a projectile, and the tangent normal if you have a body that is moving on a curved path, and this curved path has a changing radius, like the radius is to be changing while you are moving. And you guys remember, I told you, you have to remember A normal. Do you guys remember? What is the value of A normal? I told you have to memorize it. V squared over the radius. And actually, I told you this is very, very important, especially who you're civil engineers, right? If you are gonna specialize in transportation, all the transportation people rely on this rule. Like all their curves and all their design. You know, when you driving on a curve, what happened is, like let's say that you are on the highway, I-75, and you want to take an exit here, something like this. So this is a curve. Here you are maybe driving your car 70 or 80 miles per hour, and once you hit here, you will find a sign that tells you you have to slow down to 45 miles per hour. Why? Because you are entering a curve. And when you enter a curve, if your speed is very high, this speed is gonna be square, and you are gonna have a normal acceleration that is very, very high that needs you to take you out of the curve. So you have to maintain, like when you're entering the curve with very high speed, you feel that your car wanna be thrown out of the curve, right? Because your car wants to be on a straight line. Your cars or driving or going very fast doesn't like to be on a curve. Once you hit the curve, your curve wanna throw you away to be on the straight line, but you have to maintain a normal acceleration so you can be on the curve. And to make the force on the car less, you have to make the velocity less, because we know, like what happens here, if your car is moving here, and you are moving with a specific speed, your car wants to go back to the straight line movement, and there is a force here, it's throwing you away. So we need to find a way to counter this force with another force to bring you back to the curve. So if you want to make balance here, not going this way or not going this way, you have to find a way that can maintain you a normal acceleration here on this curve. So basically, when you are driving with 17 miles per hour, once you hit the curve, it means you like slow down to 25 miles per hour so that you can make the normal acceleration lower and you can have low forces on the car. If you drive so fast and you enter your curve, if you will not be able to hold all the force that are on your car and you just like somehow you couldn't resist it, your car is gonna be thrown away to the straight line curve. So that's what happens here. That's why usually when they design curves in transportation, they make super elevation. Do you guys know what a super elevation is? Like the curve is always, like if I take a cross section here, you'll find that the road is not straight line. Like if the curve is that way, you'll find that the road is something that way. And you drive your car so that a component of the weight goes that way to balance the normal acceleration that you have. So your car wanna go out of the curve, but your car wanna slide down because of the slope. So it helps you better to be on the curve because it adds, rather than all the force to be on you, so no, but the weight of the car wants to go down with you. Okay, so that's one thing. That's why when you have races, like there's the Formula 1 or something, you make these slopes are very, very steep because they drive so fast on a very tiny, narrow radius, and they make it because they need all the components go that way. It's almost vertical. Okay, so that's why like if somehow you find a car, I mean I don't know, like maybe like if a car is entering a curve and somehow you made the super elevation 90 degrees, if you are driving very, very fast, you can drive with your car that way while it's vertical, not this way. But if you stop, it's gonna flip. Why? Because the centrifugal force is not gonna be there anyway. Okay? So that's kind of an application. That's why I don't want you, every time that you are hitting a road curve, remember this rule. It's a v squared over rho. If the radius of the road is not like, it's a small, so you will find that this is speed, like somehow, when we make the radius of the transportation network, we take a lot of factors. If you are in, like there's a lot of houses that you cannot make your radius very big, so you have to make the radius very, very small. So you will find the speed is 25 miles per hour. So the speed is very low. But if the radius is big, like it's almost a straight line, you will find that that it allows you to go up to 45 miles per hour on the curve. Why? Because the curve is very big, like the radius is huge. So if the radius is small, that is gonna make the normal acceleration bigger, so you have to slow down. If the radius is big, so that means that the normal acceleration is low, so you can increase your velocity. What if the radius is infinity? That means there is no normal acceleration, and that means that you are moving on a straight line. So the line, if you have a straight line, the radius is infinity. So if you substitute here with infinity, that means that there's no normal acceleration. So basically, let's say that you are on a curve and you're hitting the road. So here there is normal acceleration, normal acceleration. Once the radius is infinity, there is no normal acceleration and you are moving on a straight line. That's why I keep telling you, always remember this rule, that normal acceleration is v squared over the radius. So this is going to take us to, what about the total acceleration? As you know, the total acceleration has two components, has tangent in the ut hat and has normal in the un hat. So the un, the normal, we know it. How about the tangent? The tangent is rho theta dot ut hat plus v squared over rho in the un hat. So basically, you can deal with the tangent component like you are moving on a straight line. Like the tangent component, like I'm saying, this car is moving with a velocity this. The velocity is in the tangent. There's no component in the normal. And you are speeding with 5 miles per hour square. So that's still a tangent acceleration. And you can apply all the rules of the linear acceleration in the tangent direction. This direction, on the road. But the normal direction, you cannot apply these rules. Okay, the normal direction has one rule, v squared over rho. Okay. All right, so right now I'm gonna take you to a different coordinate system, which is the polar coordinate system. What if the radius is not changing? Your radius is constant. And right now, if my radius is constant, I'm gonna take you to the polar coordinate system where we have r and theta are changing. So let's see how this is gonna look like if we have a curve. Let's say I have, this is my x-axis, and this is my y-axis. And this is my curve. And you have a body is moving on this curve. And this body is here. Okay, so the first thing before we start any coordinate system, what we do is we try to map the coordinate system. So right now I have x-axis. If you guys, last time, what we did, we said that if my body's here and is moving that way, we said that this is the tangent direction, t hat, and the normal direction is always perpendicular to the tangent, and it's always inside towards the center of motion, okay? That's t hat and n hat. How about if I want to move to r and theta? Look at what r and theta is going to be. So r and theta, this is the r vector. This is the position. We call this R vector. So the R direction, so usually R is in the same direction of the position, going that way. That's the R hat direction. If you want to find out the theta direction is perpendicular to R in the direction of increasing theta. So let's say my body's here and then moved here and moved here. So R basically is moving that way. So this is the increasing direction of theta. So you tell me, is theta that way or that way? Is it up or down? Up, okay? So theta is that way, right? In the final exam, and maybe in the midterm exam, I'm gonna ask you, if you have a body is moving on a curve, map the tangent normal, map the R and theta, and map the XY, okay? So you have to map all of these. This is how I map, like, let's say that my curve is something like this. Let's say my curve is something like this, and this is my body. So the tangent, and my body is moving that way, so that is the tangent direction, and that is the normal direction. And let's say my XY coordinate system is here, and this is where my body at, like let's say it's something like this. So R is in the direction of the R. This is the R hat direction, and it is in the direction of the increasing theta. Let's say that my body is moving that way, so theta is moving that way. So that is theta, okay? So right now I map both the tangent normal and the R and theta. Let's put it here. Let's say that my body is here. So my tangent is that way. That's the tangent, and that is the normal. And let's say that here's the center that I'm looking at. So this is R. This is the R vector, the position vector. So this is the direction of R. This is the R hat. And theta hat, let's say that my body is moving up, so this is the direction of increasing theta. So theta is perpendicular to the R in the direction of increasing theta, so this is theta hat. So this is how I map the two coordinate system on the body. Do you have any questions on the mapping? All right. Okay, so here I said that R is the radial axis, goes from the origin through the particle or through the body. That's the R vector. The theta is the transversal axis. It's always perpendicular on the R axis in the direction of increasing theta, and that's what we did. So I'm saying, like, if the motion is restricted to a plane, then polar coordinate system could be used. Like if you know it's gonna move on this circle and this circle has a constant radius, so you use polar coordinate system. Polar coordinate system has a non-moving origin, so the origin is constant, it's a point. However, R and theta can be changed. So R and theta can it change? You will tell me, well, theta may be changed, but how R can it change if it's the center is constant? I'm gonna tell you we're gonna have a problem where R is changing while the center is constant. Because if you have a circle, if a body is moving on a circle, so R is constant in magnitude, but in the direction, keep it changing. And the thetas keep it changing because every angle is going to be different. When you have R here, the theta is here. The theta is moving that way. So we are going to see how this looks like in a little bit. But let's first find the kinetics, the kinematics of the motion. Like let's find the position, the velocity, and the acceleration. It's going to take us like 20 minutes to do every one of these. Okay, let's first start talking about the position. So position, R vector, is going to have a component, let's say, stick to the terminology that we have here. It's going to have R as a magnitude and all the R as a magnitude in the direction of the R hat. So this is the position vector, R vector. So all the position vector magnitude has a magnitude R, and it's in the direction of R hat. So I can say this is R in the R hat direction, plus 0 in the theta hat direction. So the position vector as a whole is in the direction of R hat. There is no part of this is in the direction of the theta hat. Okay? Does we all agree on this? all the r vector is in the r hat direction. There is nothing in the theta hat direction, so this is 0. All right, how about the velocity? The velocity here is not like the tangent normal. In the tangent normal, we said before that the velocity is always tangent to the direction of the motion. And it still applies here. It's always the velocity is in this direction, v. But right now, v is all in the tangent direction. But right now, I'm not dealing with tangent normal direction. I'm dealing with r and theta direction. So I have to find the component vr and the component v theta. How? By finding this angle, and then I do v cosine and v sine and find the component in the r and in the theta. So if we want to find them, the v vector is going to be equal to vr in the r hat direction plus v theta in the theta hat direction. If this is tangent normal, v is equal to v vector is going to equal to the magnitude and all the magnitude in the t hat direction. There is nothing in the normal direction. Okay, so that is the velocity. But we all know that the velocity is the time rate of the change of what? Of the position, right? So if we differentiate this with respect to the time, we can get the value of vr and v theta. And I need you to focus with me on this part. I need to do something first before I write it so you can understand. But we did something similar last time. Okay, let's say I have a circle, and this is the center of the circle, and my body is here, and somehow this body moved and came here. So this is the first position, and this is the second position, and that happened in a really, really small time interval, and I was able to cut a little bit of a radial angle d theta. And if the radius of the circle is rho, and this is the distance ds, let's say, yeah, that's rho, and this is d theta, can you guys tell me, based on what you learned last time, what is ds equal to?
d theta times rho.
Rho d theta. The radius multiplied by d theta, the same concept of the perimeter or the circumference of the circle. So ds is equal to rho d theta. That's what we learned last time. But right now, I'm going to do the same thing that I did in the tangent normal on r theta. So let's find the r theta hat direction at this position. Actually, r is always in the direction. Here's my body, and here's the center. This is the r vector, so this is the r hat. I want to make sure that I'm using ur or ur hat. Okay, let's use, by the way, here I put r hat and theta hat. It is the same if I put ur hat or u theta hat. They all, and sometimes we write er. So ur or er, it's all unit vectors. Okay, so if I, just to be consistent with the notes, I put here r hat and theta hat, r hat and theta hat. So I'm gonna put ur hat and u theta hat. Okay, that's the unit vectors that we're going to use in this objective. R hat and theta hat is fine, but just like not to be confused with here. So here, this is the direction of ur hat. Okay, if the body's moving down, so this is the direction of increasing theta. Where is the theta hat direction? That way, right? This is the theta hat direction. Here, this is the ur hat direction, and here is the u theta hat direction, but I'm gonna say this is dash and this is dash because this is the first and this is the second. Okay, so let's see how the unit vectors got to change it in magnitude and direction, because the unit vectors were here. So I'm gonna represent, this is my unit vectors, like this, and then they kept moving and be here. Unit vectors are always, they don't change in magnitude. Their magnitude is 1, but they keep changing in direction. So here they are like this, 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 so they keep it changing in the direction. So here, this is the UR. Right now, if I came down, this is the UR. Like, let's say UR here is gonna go up. This is the UR hat. Here is gonna be that way. So it's always outside of the circle. So I want to see how they are changing. What is the DUR hat? That's what I want to find out. DUR hat and DU theta hat. That's what I want to find out, how they are changing. Okay, so I'm gonna put them that way. This is at this position, U theta hat, and this is U R hat. And then I'm gonna put the second position. For the second position, this became something like this. This is U R hat dash, and this is U theta hat dash. So they were here, and then they changed it in direction. So they became something like this. So they changed it in direction. So I want to find this a change. All right. So the angle of a change is the d theta. So this is d theta. So if you guys remember from last time, if you want to know the change in UR hat, this is the change. UR changed, it moved it from here and became here. That's the change. U theta hat, it changed from here and moved to here. That's du theta, and this is DUR. So I want to find the value of this change. Okay, let's find as a value and magnitude. DUR hat is going to be equal to, that's like a circle. So this moved from here and came here. So that's the radius of the circle, and that's the angle that it moved. So if we want to find the distance, so it is the theta multiplied by r. So I have d theta multiplied by the magnitude of the radius, which is the UR hat magnitude. That's all as a magnitude. Forgot my water bottle. Just 1 minute. I'm gonna drink water and come back. Okay. Right, so I want to find DUR hat as a magnitude and direction. As a magnitude, I multiply d theta by this value, so I get the magnitude of this, and I know that the magnitude of any unit vector is 1. So it's only d theta, but what is the direction? The direction, if you look at this, DUR hat is in the same direction of u theta hat. So this is this way, and this is this way. So this is in the direction of u theta hat. Similarly, if you want to find du theta hat, is going to be also equal to d theta, but in the magnitude of u theta hat, which is 1, in the direction, look at this. This is going up du theta because you move from here to here. And UR hat is going down, so this is in the negative direction of UR hat. Okay, so what happens here? UR hat moved from here to here, so it moved that way in the same direction of u theta. But u theta hat moved from here to here, goes up, and UR hat goes down, so it's in the negative direction. Anyway, all what I want from this, I want to say that DUR hat is equal to d theta in the direction of the u theta hat, and du theta hat is equal to negative d theta in the UR hat direction. That's what I want from all this geometry. Okay? If you don't understand it, just put this in your mind. Okay, let's get back here. DUR dt. We are going to use this concept here. That's why I'm making all this just to solve this. The velocity is the time rate of a change of position, and you already know what is the position vector is. The position vector is an r in the direction of UR hat component. And the thing is, that's the two variables. You have variable 1 and variable 2, and I taught you last time, if you have function fxy, and x and y are both variable, you have to differentiate variable 1 and multiply with variable 2, plus the differentiation of variable 2 multiplied by variable 1. So if I want to differentiate this, so this is going to be equal to the differentiation of r, so this is going to be r dot in the direction of the UR hat, plus r itself without any differentiation, DUR hat dt. Okay? Look at DUR hat dt, I'm going to take it here. DUR hat dt. I already know that DUR hat is equal to d theta u theta hat. So basically, I'm going to divide this equation over dt. So it's going to give me d theta over dt in the direction of u theta hat. U theta dt is theta dot in the u theta hat direction. So that's why I did this part, so that I can come up with this equation. So basically, I can write this as r dot in the UR hat direction plus r multiplied by theta dot in the u theta hat direction. So right now I have the equation of the velocity that way. How about the acceleration? So what is the definition of the acceleration? Is the time rate of a change of velocity. So I have here acceleration. All right, that's a little bit difficult, but we're gonna do it. As we said, that the acceleration A is the time rate of a change of the velocity, dt. So what should I do? What I'm gonna do? I have this, and I need to differentiate this, but this is gonna be the most difficult differentiation because right now, this one is going to be two variables. So I differentiate this by this and differentiate this by this. I finish that part. Plus, the differentiation of the first variable multiplied by the other two variables. The differentiation of the second variable multiplied by the other two. And the differentiation of the third variable multiplied by the other two. So can you guys do it and tell me what's right? I just want to know that you guys know how to differentiate, okay? So let's do it together. What should I write?
R2 dot.
R double dot. Why? Because I differentiated this with respect to dt. So it's going to give me R double dot. Multiplied by UR. Plus
R dot.
R dot multiplied by
Du.
UR hat. Sorry. Multiplied by DUR hat dt. So what I did, I differentiated the first multiplied by the second. Plus the first differentiated multiplied by the differentiation of the second. I finished the first part. Let's do the second part, which is much more difficult. It's gonna be differentiate the first variable. R dot multiplied by theta dot u theta hat. I didn't differentiate the other two. Here, what I'm gonna do? R theta double dot, and then you have u theta hat as is, plus r theta dot du theta hat dt. Excellent. So I have three terms because I have three different variables. I differentiate the first multiplied by the other two, the second multiplied by the other two, the third multiplied by the other two, and then I have this. Okay, right now I need to do some substitutions. Do you guys remember what we did here? We found that DUR hat dt is equal to this. We can, the same part, du theta hat dt, if I divide it by dt here, is going to give me negative theta dot let me write it as a whole. So if you guys know where this is coming from, if I divide this equation by dt, is going to be negative d theta dt ur hat, and this is going to be equal to negative theta dot ur hat. So what I'm going to do, I'm going to substitute with these two here. So what I'm going to put here, theta dot in the u theta hat, and this one is negative theta dot in the ur hat. That's why I was doing all this calculations that I was doing over there. So when you have an equation that is function in many vectors, we take the vector as a common factor and see what quantities that are sharing the same direction. So I have r double dot in the direction of ur hat, and I have r theta dot multiplied by negative theta dot also has a ur hat. So I can say that the acceleration A is equal to r double dot minus r theta dot square, because when I multiply theta dot is going to be squared, and all this in the direction of the ur hat. Let's put the theta. In the u theta hat, I have r dot theta dot, and another one r dot theta dot. So I have two r dot theta dot, and I also have r theta double dot. So I can put r theta double dot plus 2 r dot theta dot, all this in the direction of the u theta hat. Let's make sure that we have all the equations right. Okay, we are good. All these equations are in the equation sheet, but you should know where these are coming from. So if you know where are these coming from, you will be able to solve question. I'm not going to ask you in the exam to prove these, where they came from, but you should be able to know how to use them. Okay, so you should be able to know what is every one of these. Yeah, r double dot is the double integration, the double differentiation of the r with respect to t. So I give you r as a function of something, you differentiate it once and you differentiate it twice, and we call it the radial acceleration. And this is the position, and this is the angular velocity, and this is the angular acceleration, okay? And this is the angular, the radial acceleration, and this is the angular acceleration. So the body have a position, and this position has angular velocity and radial velocity, angular acceleration and radial acceleration. So all what I want from you is to know how to use this equation, the velocity equation, and the acceleration equation. Okay, let's say that we have an example. That you went to, for example, like a carnival or amusement park, and you were on a carousel, something like this. Let me ask you, if you are on the right here, and you are connected on a bar, and you are sitting on something here, and this is start spinning, and this is R. R is constant, right? Your radius is constant. Radius is not changing, unless somehow this game has a bar and the bar is telescopic, and while you are moving, this is keep moving out and in. So that means R is a changing, but let's say R is constant. So if R is constant, what is the value of R dot? 0. What is the value of R double dot? Is 0. So right now we are going to have a reduced velocity vector. The velocity vector is going to have R dot is going to be 0, but R is constant, so this is going to be R theta dot in the direction of the u theta hat. The acceleration, this term is going to be 0, and I'm going to end up with just this term, negative R theta dot square in the direction of the u r hat. This term is 0, and I'm going to end up with this term, which is R theta double dot u theta hat. All right, So that means if the r is constant in a problem, these equations are gonna be reduced and are gonna be in this form. But sometimes our problems have variable r, so sometimes this doesn't apply. But if it applies, let me see. I solved it here, I forgot the negative. So I'm not sure if it's right, because I wrote this yesterday at night because I had a missing one page in the notes. But maybe you guys check the notes that is uploaded. This should be negative, okay? I mean, like, this is right. I mean, like, in the notes, maybe it's not right. Okay, and r theta dot, so yeah, everything is right. Let's see an example that r is changing. So let's see how r can change. Let's say that we have a bar. And there is like a thread here in this bar. And you have a small bar inside. And there's like something is moving on that bar inside and out. So let's see what happens here. This is my body, and this body can move along this line, and this can move radially. Like here, I believe it starts from here, and this is my angle theta. So start from here and go all the way here. So in the same time, this bar is moving that way, and there's something on it that is moved radially. So that's when we have a changing radius. So I gave you in this example that this body started at theta equal 120 degree, and the angular velocity is 0.1 radian per second, and the angular acceleration is negative 0.04 radian per second squared. So I give you everything about theta. Theta, theta dot, theta double dot, everything you have. And r is it changing with theta. R is equal to 2 sine theta. That is the equation of r. So this is how r is changing. Here r was constant. So r dot, and r double dot is were zero. So right now I give you r, and what I'm asking you is to drive the velocity and the acceleration vector. Okay, to drive the velocity and acceleration vector, I already have them here, and they are already in the equation sheet. So all what you have to do to get the equation sheet and write these two equations. And you're already given theta dot and theta double dot. So all what you have to do is to find what is the value of r, what is the value of r dot, and what is the value of r double dot. If you found them, you will be able to solve this equation. Okay? Right, let's see how we can find them. And I want you to find them at this instant, at theta equal 120 degree. So you tell me, what is the value of r at theta equal 120 degree? It's gonna be 2 sine 120, right? That's direct calculation on your calculator. So this is gonna be 1.73. Okay, let's get to the difficult part. What is r dot? dr dt. Right, what is it? 2 cosine, right? 2 sine theta, the differentiation of sine theta is 2 cosine theta, but it's missing something. This is right if you are differentiating this function with respect to theta. But I'm differentiating this function with respect to the time. If you're differentiating this function with respect to theta, it's gonna be at the end you are gonna write d theta, the time rate of change of theta with respect to theta at the end. But let me make sure that, yeah. So, but d theta by d theta is 1. The thing is, I'm not differentiating with respect to theta, I'm differentiating with respect to t. So at the end, I'm not sure, maybe this basics is a little bit shaky in your background. You guys, I talked about this before. If we have a function y equal 5x squared plus 2x plus 1. Back in the days when you were doing differentiation, you always be given differentiate this function with respect to x, dy dx. So what you do is, you are going to say this is 10x plus 2 plus 0, right? That's totally right. Why? Because you're differentiating with respect to x. After you differentiating every function, at the end, you have to write, after you finish, you have to write this, dx, and put here the number, here I put dx after each part, and here I put the variable that I'm differentiating to. And then 2x multiplied by dx dx. And this is going to be 0. But the thing is, back in the days when you were differentiating this, you didn't write that because you know that this is 1. What is the time rate of a change of x with respect to x? It's 1. It's the same variable. So, back in the days, you didn't write x dx dx, and you just like said that is 10x plus 2. But here, right now, I'm not differentiating this function with respect to x. I'm going to differentiate this function dy with respect to completely different variable, t. It's not even in this function. So I'm going to do the same thing. It's going to be the same number, 10x, but at the end, I'm going to write rather than d. So I'm differentiating with respect to dt, so I'm going to put ddt, and then I'm putting the variable that I'm differentiating to, dx dt. Same thing here. This is going to be 2 multiplied by ddt, and I'm differentiating x, so I'm going to put dx dt. Okay? Same thing here. If I'm differentiating this function with respect to theta, this is going to be right, because here at the end, there's going to be d theta with respect to d theta. Okay? But right now, this is not theta, this is d dt. So here, I'm going to remove theta and put t. Okay? This is very basic in differentiation. Okay? All right. So this means 2 cosine theta multiplied by theta dot. Okay?
And the unit vector? Was the unit vector?
No, we are going to keep it that way. There's everything here right now is not in a unit vector. Everything here is like
So you don't replace
magnitude.
that for that?
After we finish, we are going to put every variable here, and then the unit vectors are going to show up. You see here, this equation? So we are going to getting the quantitative parameters, and we are going to put them together, and then, because we already finished the vector analysis here, when we proved this problem. So all this is not going to show again. All this, we did it so that we can come up with a general rule that we can use. All right, so the second derivative of r dot is going to be a little bit more difficult. Why? You tell me why. If I did the second derivative, it's going to be difficult because right now we have 2 variables. Before, you only have 1 variable. So here, I have to differentiate this and multiply by this, and then differentiate this and multiply by this. So you guys tell me, what is the differentiation of cosine theta? Let's differentiate this part first. -2 sine theta, and don't forget d theta dt, right? Once you finish, because this is not with d theta, this is with respect to dt. And then you multiply by theta dot that is outside, okay? Plus 2 cosine theta, and then you are going to differentiate theta dot with respect to the time one more time. So this is going to be equal to theta double dot, right? So because this is d theta dt, when you differentiate one more time, it's going to be the second derivative of the theta. So at the end, I'm going to have, this is actually is theta dot. So you are going to have -2 sine theta multiplied by theta dot squared plus 2 cosine theta multiplied by theta double dot. So when you want to get r double dot at theta equal 109 degree, so basically you are going to substitute in these parameters. So you have theta dot, you have theta double dot. So you put all of them here. So you're going to get that r double dot is 0.0227. Okay, did I solve the problem? No, still. If you want to solve the problem, I want you to find V and to find A. So let me see where can I continue this problem. I'm going to continue this problem here. Okay, so I want to find the velocity. So the velocity equation is r dot in the u r hat plus r theta dot in the u theta hat. So I have r dot. Basically, you can substitute here with theta dot, so you'll find out that this is equal to negative 0.1. So we have here negative 0.1 in the direction of ur hat plus r multiplied by theta dot. So you have r 1.73 multiplied by theta dot, it's 0.1, so it's gonna be 0.173.
Positive or negative?
This one? This one is negative here. Why?
That was positive.
Which one?
No, when you write it, the information.
That's for theta dot.
This, which equation?
Oh, theta dot. Oh, no.
This?
No, no,
Right?
no,
Okay, alright. Okay, so here I already find the velocity. So the second part is to find the acceleration. The acceleration is going to be equal to this equation, r double dot minus r theta dot square in the direction of ur hat plus r theta double dot plus 2 r dot theta dot in the u theta hat. So once you substitute those all, you have all the numbers. You have theta dot, theta double dot, r dot, r double dot. So once you substitute, you will find that this value is 0.0054 in the direction of ur hat plus minus, sorry, 0.0892 u theta hat. Okay? So right, let's see. Yeah.
Is it 1.73 times u hat theta, or is it 0.
You are talking about this r theta dot, or which one?
The line under that.
This?
Yeah, when you plugged it in, r theta.
This?
Yes.
This is r theta dot.
Yeah.
Okay? So r actually is r is 1.73 and theta dot is 0.1. So 0.1 multiplied by 1.73, it's like 1.73 over 10, so it's gonna be 0.173.
Okay.
Okay, so let's talk about this problem and see if it's difficult or easy, okay? So this problem, I give you r as a function of r equal to 2 sine theta, and I give you the 3 values of theta, theta dot, and theta double dot. So all what you need to solve a curvilinear motion using polar coordinate system, you need the r's, you need the thetas. R's is already, thetas are already given. R, it's a function. So to get r dot and r double dot, you have to differentiate 2 times. If you differentiate it 2 times, the problem is done. But the thing is, you have to differentiate it right. And I taught you that in differentiation, if you are differentiating with respect to the variable other than the variable of the equation, you have to put ddt or dd theta at the end, okay? And in dynamics, we are dealing with time all the time. So we always differentiating with respect to the time. So I just want to test this one last time and make sure that you guys got it all. If I have a function c equal to y cubed plus 2y squared plus 7 a bit tricky. I'm not going to differentiate with the time. And I want you to find dz dx. What is the value of dz dx? Can you guys start? Differentiate this. I just want to make sure that you guys, it's the same regular differentiation like any function. How you differentiate y cubed? 3 3y squared. That's right. Like differentiating any function, but at the end, dy dx. Excellent. Why? Because at the end, I have to put what I'm differentiating to, dy dx. But you know what? If I'm asking you to differentiate this with respect to y, here it's going to be dy dy, and this is going to be 1, and it's going to be 3y squared. That's the thing that you learned before. But right now, here we are differentiating with respect to different variables. So at the end, you have to put d dt, or whatever the variable that we are differentiating to. So let's get back to dx. So make sure before you differentiate any function that you look at the variables that you are differentiating with respect to. So I'm differentiating with respect to x, so I'm going to put dy dx. What is next? 4y and dy dx. And then 0. That's it. Okay, if I'm changing x to t, so this is going to be dy dt, dy dt. This is very, very important. That's actually what I did here. I differentiated this function. If I'm differentiating this function with respect to theta, so this is going to be 2 cosine theta. That's it. Because at the end is going to be d theta with respect to d theta, and they are going to be equal to 1. But I'm not doing this. I'm differentiating with respect to the time. Dot means that we are taking d dt. So at the end, you have to put d theta dt, and they are not equal to 1. Okay? D theta dt is equal to theta dot. And right now, we generated another variable in the equation that you have to differentiate one more time if you are going to take r double dot. All right, so is this, I have another example for you from the textbook, one of the unsolved example, and I solved it here. So when you go home, maybe you open the textbook and get example 1293 and try to read the problem and solve it, and then check your answer. Alright, so now I'm gonna start something that's called dependent motion or constrained motion, and it's a very, very simple concept. Maybe it's much easier than all of these things that we are doing because it has a lot of differentiation. Even though we are engineers, but I don't know, somehow engineers doesn't like differentiation and integration. But you guys, I believe you guys got a lot of integration. You studied even partial differentiation, right? And partial integration and all these stuff. So I mean, like, you guys should be fine. Okay, so let's study dependent motion. So what is dependent motion? It's still bodies that are moving and we want to study, but they are dependent on each other. How? So the famous example is the pulleys. So what about them? So let's say that we have this system of pulleys here. I have 2 of them are fixed to a fixed space, like a fixed line or a fixed wall or a roof. And then we have a cord is extended that way. The cord is like this and go over this body, and then this body, and then go to this one, and that way, and then going back to the fixed location. All right? And the thing is, what I have here, I have a body here. Let's say I have body A, and this pulley is pulley number B, okay? So, I gave you, for example, the velocity of this. Let's say I give you that this weight is moving down and this is VA, and I want you to tell me what is the velocity of this pulley, VP. So definitely, why did I draw it up? And that's like the intuition. If you pull this body down, so all this wire is gonna go down, and this body is gonna go up, right? It's not gonna go, like let's say that we have an attached weight to this body. Let's say I put a weight here, and I call it V. So the weight V and the pulley system, they are going up with a velocity VB. But the thing is, how we can find the velocity? Let's say that I told you that the velocity of this weight is going down with, I don't know, 1 meter per second. What is the velocity of this body? How we can find it? This is the strategy to solve this problem. I'll make sure that I cover it. Okay, so I'm just saying that dependent motion means that connected particles that must move together. Like the motion in one body is gonna trigger the motion of another body. That's the meaning of the dependent motion. And how to solve this system? We do a little trick. We try to find a fixed line, like this line. But before I do this, let me tell you something. This cord, or this rope, has a constant length, right? It doesn't change in length. If you pull it down, or if it goes up, it has the same length. It's not gonna change. So what I know, that this distance, plus this distance, plus this distance, plus all this part and all this part are equal to constant. Or, like let's say, I'm gonna name these two pieces, like from here to here, here to here. This, I'm gonna name it like L1, L2, L3, L4, L5. What I know about this, that L1 plus L2 plus up to L5 equal to constant, right? The length of the rope. But I can do something else. The thing is, I know that there's some pieces are constant, I'm never gonna change. Whatever this is goes down or this is goes up. This piece is gonna stay there, and this piece is gonna be always here, so this is gonna be always constant. But what is changing in length? This part and these two parts, right? Because if this goes down, these two parts are gonna go down. And they are gonna take from this length, and this length is gonna go up, right? So the changing lenses here is this lenses, like the lens from here and the lens from here. So also I can say that L1 plus L3 plus L5 are equal to constant. Why? Because if this goes up, it's gonna give more length to L5. So I can say that they are equal to constant. But let me put this equation that way. I mean, like how to solve problems. Solving problems, you need to find a fixed axis, and I know that this is a fixed line, this part. So all this is a fixed line. These points are not gonna change. This pulley is not gonna move. It's fixed here and fixed here. So that's a fixed line. And then I will start to measure the length to the moving parts. I have this body's moving, so I know here, this is the first moving body. I'm gonna say that this is YA. And I know here, this is YB in the center here. So I can say for this body that YA plus 2YB are equal to constant. This plus this part are equal to constant. Okay? And if I know that these lenses are equal to constant, if I take the derivative of this equation with respect to time, so I'm gonna end up with dya dt plus 2 y dyb dt the differentiation of the constant is gonna be 0. So the velocity of A plus 2 the velocity of B are equal to 0. And if you know the velocity of A is 1 meter per second, and make sure it is in the same direction of YA, so I put here, this is 1, and it's gonna be 2 VB equal to 0, so VB is gonna be equal to negative 1 over 2 meter per second. Okay? So this is how we solve the dependent motion. I'm gonna solve another example to make sure that the concept is, so, all right, so the main concept of dependent motion is to try to find, it's all dependent that you have one chord that should be the same length and is not changing. And it's always equal to constant. But what I did here, actually you can put all these pieces, like you can actually say that this L plus this, plus this, plus this, plus this part, and this part, you can divide it into 10 pieces, and you say all these pieces are equal to constant. But the thing is, let's do it that way. Maybe you guys, some of you didn't understand it. Like, let's say the same pulley system. I already solved this problem, but I'm just going to do it in a different way. All right, I'm gonna divide this into pieces. I'm gonna say that this piece is L1. I already have this as YB. And I'm gonna name this piece as L2. And this is already YB2. And I'm gonna name that piece to L3. And I already have this. Can you guys tell me what is the length of this chord? L1, right? Plus YB. Plus L2. Plus another one YB. Plus L3. Plus YA, right? Equal constant. The length of the rope, let's say it's equal to L1. The length of the rope, it's equal to constant, right? If I take the derivative of this function with respect to t, d dt, anything that is constant in this equation is going to be 0, right? And anything that is variable over the time is going to stay variable and it's going to be differentiated with respect to t. During the motion, let's say this body went down all the way here and this went up. Is this part is it changing? This part is going to be always constant. From here to here is going to be always constant. It's not going to change. What is going to change is this part from here to here is going to go up and down. So basically, if you differentiate this with respect to t, it's going to be 0. And if you differentiate, this part is changing over time. Like if you pull this down, this part is going to keep changing. Like it's going to go up and down. So you're going to end up with having this and this as 2 dyb dt. L2, this part is not going to leave anywhere. If this body goes up or goes down, this piece are going to stay here. It's not going to leave the pulley. All right? It's gonna stay here. So this is going to be always constant. So the differentiation of L3 is going to be 0. Same thing. This body, let's say that this body moved up. If it's moved up, there is always be part of the chord is going to be here. It's not going to be shorter in length. Like these two are not going to get closer or are not going to stay away from each other. So there's always be a part here in this area, and there's always be a part here. All what is it changing in length? Like let's say this body went a little bit down here. So this got taller and this got smaller. So these pieces are the only pieces that are changing in the length. Okay? This is not changing, this is not changing, so you will only end up with having dya dt is equal to 0. So this and this. Let's do this on a much complicated problem. Like what if you have two cords connected to a system of pulley? Let's say that we have, this is a fixed surface, okay, and then I have one big one here. These are fixed, but they are not moving, and this is fixed here, and this is fixed here. All these are fixed. These are the two moving ones. And let's see how many chords that we have that connects them. So we have one. The first one is starting from here and goes all the way up and goes around this bully and then goes here and then goes here and then goes here until the center of this one. So that's the first chord. The second chord is starting from here. From here and goes all the way here and then rotate around this and goes around this and then goes like this and then you have a body here. Okay, so you have two of them and you have another body connected here. This is body B and this is body A, right? So the thing is, first thing that we need to do is to find a fixed axis that we can measure the distance from. So we have two moving bodies. If you have two moving bodies, so you have two velocities. Here it's the same. I have two moving bodies. I have velocity here and velocity here. Here I only have actually three. I have this one and this one and this one. I have three bodies. Okay? But I only have two equations because I only have two chords or two rock here. This red and green. So definitely, one of these variables should be given. So I have in this problem, the velocity of this body is 1 meter per second. And it's going up. The velocity of A is 1 meter per second, and it's up. But tell me, if this body is moving up, what do you think about body B? Is it going to move up or move down? This is going to move up. So this chord is gonna go down, and then this is going down, all this is gonna go down. So definitely B is going down. All right, so let's find out how we can find the magnitude of the velocity. So let's do it very quick. First, I have to find a fixed axis. I know that this is fixed. And then I need from this fixed axis to measure to the center of the bodies that are moving. So first I have this body. This is, I'm gonna name it Y1, and this is the second body. This is, I'm gonna name it as a Y2, and this is the third body, I'm gonna name it as a Y3, okay? All right, so let's find out the pieces of the chords, like the lenses of the chords that are moving. So I know that this and this and this are part of the red chord. So I want to find the lenses of these ones. So how can I find this? Actually, it's a Y3, and another Y3, and here, from here to here is Y3 minus Y2, right? So I can say that this is 2Y3 plus Y3 minus Y2, right? That's the moving lenses of this chord. If you want to add the piece that is here and the piece that is here, that's fine, okay? So that you can say that all of these are equal to the length of the road. But I know that the length, this length, and this length is constant. So when I differentiate them, it's gonna be 0. But you can put them. So you can say that this row is this part, this piece, which is Y3 minus Y2, plus this part, plus Y3, plus this part, plus another Y3. Okay, you can put all of them here, but you can end up with another 2 constant. All right, so I'm done with equation number 1. Equation number 2, I have this. Okay, so I have here Y2 and another Y2 and another Y2, 3 Y2s, and Y1. So I have 3 Y2 plus Y1. All these are equal to constant. Okay, how did I come with that? With this? Here is a start from here. It goes Y2, and then goes constant length, and another Y2, and a constant length, and another Y2, and a constant length and another y1. So I put the second equation. So right now I can say that I have 3y3 minus y2 is equal to constant, and that means that 3v3 minus v2 is equal to 0. And this one is 3v2 plus v1 is equal to 0. How can I solve this? I already have the velocity of number 1. It's going up, it's negative, because that's the positive direction of y1. That's how I assume it. So v1 is equal to negative 1 meter per second. So if I substitute this here, it's gonna give me 3v2 minus 1 is gonna be equal to 0. So v2 is gonna be 1 over 3. I know v2, so I can substitute here. So 3v3 minus 1 over 3 equal to 0. So v3 is gonna be equal to 1 over 9, and it's positive. So that means that b is moving down with 1 over 9 meter per second. Okay, so maybe when you go home, you try to put this, try to solve it on your own, and next time maybe I'm gonna solve 1 or 2 problems to refresh and make sure that you guys understand the concept. See you guys next time. In a few months, office hours, I will be available around 1:30 to 2:30.